The Pantheon in Rome, built nearly 2,000 years ago. Its massive concrete dome, still the largest unreinforced concrete dome in the world, has weathered countless storms, earthquakes, and centuries of climate fluctuations. Meanwhile, the highway overpass built in your city just 30 years ago, already crumbling, covered in cracks, desperately in need of repair. What did the Romans know that we forgot? For decades, scientists assumed ancient Roman builders just got lucky or worse, that they were sloppy craftspeople who didn't even mix their concrete properly. But a groundbreaking discovery, published in the journal Science Advances in 2023, reveals something extraordinary. Those mistakes in Roman concrete weren't mistakes at all. They were one of history's most ingenious engineering solutions, and they might just hold the key to building a sustainable future. Let's talk about concrete for a moment. It's the most widely used construction material on Earth, and for good reason. It's affordable, versatile, and strong. We use it for everything from sidewalks to skyscrapers, bridges to dams. But modern concrete has a dirty secret. It's fragile, and it's destroying our planet. Here's the problem. Today's concrete typically starts to degrade within 50 to 100 years. Cracks form from temperature changes, water infiltration, and structural stress. Once those cracks appear, water seeps in, corroding the steel reinforcement inside, and the deterioration accelerates. Before long, entire structures need costly repairs or complete replacement. And the environmental cost? Staggering. Concrete production accounts for approximately 8% of global carbon dioxide emissions. That is triple the emissions of the entire aviation industry. If the cement industry were a country, it would rank as the third largest emitter in the world, right behind China and the United States. Now contrast that with Roman concrete, or as they called it, opus cementitium. The Romans didn't just build structures that lasted decades. They built monuments that have survived millennia. The Pantheon, completed around 128 AD, still stands with its original concrete dome intact. Roman harbors, like those at Caesarea, remain structurally sound after 2,000 years of constant exposure to seawater. Aqueducts that once carried water across entire empires still dot the European landscape, their arches defying gravity and time itself. For years, scientists were baffled. How did ancient builders, without modern chemistry, without steel reinforcement, without any of our advanced technology, create a material more durable than what we produce today? The prevailing theories focused on the Romans' use of volcanic ash, particularly pozzolana, from the region around Naples, which they mixed with lime and aggregate. This volcanic material does create beneficial chemical reactions, strengthening the concrete over time, especially in marine environments. But that couldn't explain everything. And then there were those strange white chunks. When researchers examined samples of ancient Roman concrete under microscopes, they kept finding something peculiar: small, bright white mineral deposits scattered throughout the material. These deposits, called limeclasts, appeared as millimeter-scale chunks of calcium-rich material embedded in the concrete matrix. For a long time, these limeclasts were dismissed as evidence of poor quality control. The assumption was simple: the Romans must have been careless when mixing their materials, leaving unmixed chunks of lime in the final product. After all, modern concrete manufacturing standards consider such inclusions to be impurity signs of substandard production. But Admir Mazik, a professor of civil and environmental engineering at MIT, wasn't satisfied with that explanation. As he put it, the idea that the presence of these limeclasts was simply attributed to low quality control always bothered me. If the Romans put so much effort into making an outstanding construction material, following all of the detailed recipes that had been optimized over the course of many centuries, why would they put so little effort into ensuring the production of a well-mixed final product? There has to be more to this story. So Mazik and his team at MIT, collaborating with researchers from Harvard University, decided to investigate these mysterious white chunks more thoroughly. Using advanced spectroscopic examinations, high-resolution imaging, and chemical mapping techniques, they analyzed the composition and structure of limeclasts found in 2,000-year-old Roman concrete samples. What they discovered changed everything. The limeclasts weren't accidents, they were intentional. And they were brilliant. The key lies in the Roman production method, something the researchers call hot mixing. The Romans didn't use the slaked lime that we use in modern concrete production. Instead, they used quicklime calcium oxide, a highly reactive form of lime that's produced by heating limestone to extreme temperatures. When you add quicklime directly to a concrete mixture, something remarkable happens. The quicklime reacts violently with water in an exothermic reaction, generating intense heat. This hot mixing process creates temperatures high enough to partially transform the lime, leaving behind those distinctive limeclasts throughout the hardened concrete. But here's where it gets truly ingenious. Those limeclasts aren't just sitting there doing nothing. They're waiting for damage, waiting to heal. So how does this self-healing mechanism actually work? Let me break it down step by step, because it's elegantly simple and absolutely fascinating. First, a crack forms in the concrete. This is inevitable in any concrete structure. Temperature fluctuations, ground settlement, structural stress, or simple aging will eventually cause cracks to appear. Second, water seeps into that crack. Whether it's from rain, groundwater, or humidity in the air, moisture finds its way into the damaged area. Third, and here's where the magic begins, that water comes into contact with the limeclasts embedded in the concrete. Remember, these are calcium-rich mineral deposits that have been sitting dormant in the material, sometimes for centuries. Fourth, the limeclasts begin to dissolve in the water. This releases calcium ions into the solution within the crack. Fifth, these dissolved calcium ions react with carbon dioxide from the air or dissolved in the water. This chemical reaction produces calcium carbonate, the same mineral that makes up limestone, marble, and seashells. Sixth, the calcium carbonate crystallizes within the crack, essentially growing new mineral deposits that fill the damaged area. The result? The crack seals itself. Water can no longer flow through. The concrete has healed. To test this theory, Masic's team didn't just study ancient samples, they created their own. They produced concrete samples using both traditional Roman hot mixing methods with quicklime and modern methods without limeclasts. After the concrete hardened, they deliberately cracked all the samples and then exposed them to flowing water. The results were dramatic. Within just 2 weeks, the samples made using the Roman method had completely healed. The cracks had sealed shut, and water could no longer flow through the material. Meanwhile, the samples without limeclasts never healed at all. Water just kept flowing through the cracks indefinitely. It was proof positive. The Romans had engineered a self-healing concrete, and they'd done it 2,000 years before we figured it out. Now, you might be thinking, okay, that's cool history, but why does this matter today? Let me give you some perspective. The United States alone has over 600,000 bridges. According to the American Society of Civil Engineers, more than 42,000 of them are structurally deficient. That's 1 in every 14 bridges carrying traffic every single day. The estimated cost to repair and replace these failing structures? Over $125 billion. And it's not just bridges. Roads, parking structures, buildings, dams, tunnels, concrete infrastructure everywhere is crumbling faster than we can repair it. We're trapped in a cycle of constant maintenance and replacement, spending billions of dollars and generating massive carbon emissions just to keep our infrastructure functional. Roman structures, meanwhile, are still standing. The harbor at Caesarea Maritima, built by Herod the Great around 15 BC, has survived 2 millennia of waves, storms, and seawater corrosion. The Pont du Gard aqueduct in France, built in the 1st century AD, still spans the Garden River, its concrete piers as solid as the day they were poured. What's the difference? Durability, resilience, self-repair. If we could build concrete that heals its own cracks, that prevents water infiltration, before it leads to catastrophic failure, we could extend the lifespan of our infrastructure by decades, maybe centuries. We could reduce the need for constant repairs and premature replacements. And remember those emissions I mentioned earlier? Concrete production is responsible for about 8% of global greenhouse gas emissions. Every time we have to tear down and rebuild a structure because the concrete has failed, we're essentially doubling the carbon footprint of that construction. Once to build it the first time, and again to replace it. Self-healing concrete could dramatically reduce this environmental burden. Build it once, build it right, and let it last for generations. Fewer repairs mean fewer emissions. Longer-lasting structures mean less frequent replacement. It's a solution that's both economically and environmentally compelling. The Romans may not have understood climate change or carbon emissions, but they understood something equally important: the value of building things that last. So the big question is, can we actually apply these Roman insights to modern construction? Are engineers already working on this? The answer is yes, and the research is incredibly exciting. Scientists are pursuing multiple approaches to creating self-healing concrete for contemporary use. Some are directly inspired by the Roman lime-clast method, attempting to incorporate reactive lime materials into modern concrete formulations in ways that maintain the self-healing properties while meeting today's building standards. But researchers are also exploring other innovative methods. One of the most fascinating approaches involves using bacteria, yes, living organisms to heal concrete cracks. Specific species of bacteria, such as Bacillus bacteria, can be incorporated into concrete during mixing. These bacteria remain dormant in the dry concrete environment, but when a crack forms and water enters, they activate and begin producing calcium carbonate through a process called biomineralization. Essentially, the bacteria act like microscopic construction workers, filling in cracks as they appear. To protect these bacteria from the harsh alkaline environment of concrete and to keep them viable for decades, researchers have developed several encapsulation methods. Some bacteria are protected inside microcapsules made of polymers or hydrogels. Others are embedded in lightweight aggregate particles or clay materials that crack open when the concrete is damaged, releasing the healing agents exactly where they're needed. Another approach involves embedding polymer capsules throughout the concrete. These capsules contain healing agents, liquid polymers or resins that are released when a crack ruptures the capsule. The healing agent then flows into the crack and hardens, sealing the damage. There are even systems being developed that use shape memory polymers, vascular networks like artificial veins running through the concrete, and combinations of multiple self-healing mechanisms working together. These aren't just laboratory curiosities either. Self-healing concrete has already been used in real-world applications. Several pilot projects in Europe have incorporated bacteria-based self-healing concrete in buildings and infrastructure. The technology is being tested in parking structures, foundation slabs, and even marine environments. The challenge now is scaling up, making self-healing concrete cost-effective enough for widespread use, ensuring the healing mechanisms remain viable for the decades-long lifespan we expect from concrete structures, meeting building codes and safety standards, convincing the notoriously conservative construction industry to embrace new materials and methods. But the potential is enormous. Imagine highways that repair their own surface cracks before they become potholes, bridges that seal hairline fractures before water can reach the steel reinforcement, buildings that maintain their structural integrity for centuries instead of decades. The Romans showed us it was possible. Now we're finally learning how to do it again, and potentially even better. Let's come back to where we started, the Pantheon in Rome, with its massive concrete dome standing proud after nearly 2,000 years. That structure represents more than just ancient architectural achievement. It represents a different philosophy of building, one that prioritized longevity over convenience, durability over speed, lasting value over short-term cost savings. The Romans didn't have our advanced chemistry or our sophisticated engineering tools. They couldn't model structural behavior on computers or analyze material properties with electron microscopes. But they had something we've been lacking: a deep understanding that the materials we build with matter, that the methods we use have consequences, and that infrastructure should be designed not just for our lifetime, but for the lifetimes of generations yet to come. The discovery that those mysterious white chunks in Roman concrete were actually a brilliant self-healing mechanism teaches us an important lesson. Sometimes what looks like a flaw is actually a feature. Sometimes the old ways contain wisdom we've forgotten. Sometimes progress means looking backward to move forward. As we face the dual challenges of crumbling infrastructure and climate change, the secrets locked in ancient Roman concrete offer us a path forward. Self-healing concrete, whether inspired by Roman limeclasts, powered by bacteria, or engineered with modern polymers, represents a chance to build better, last longer, and leave a smaller footprint on our planet. The Romans built their empire on concrete. Now, armed with their secrets and our modern innovations, we have the opportunity to build something even more important: a sustainable future. Perhaps it's time we stopped seeing ancient monuments as relics of the past and started recognizing them for what they really are: blueprints for our tomorrow.